In Lesson 7.2, Integration by Parts, we'll be examining how to evaluate integrals composed of two apparently unrelated factors. Neither factor is a derivative of the other, so a u-du substitution will not work. Before we begin Lesson 7.2, I would like you to try one quick problem. So I would like you to give a shot to this derivative right here, the derivative of this function u times v minus the integral of v du. If you would like to try this on your own, please pause the video and give it a shot. When you rejoin us, we'll be working this out. As for the rest of you, let's go ahead and try this. Remember that when we differentiate uv, where u and v are both functions of x, we need to apply the product rule. Of course, because u and v are functions of x, we also need to apply the chain rule as well. And what that's going to tell us is that the derivative of uv is simply going to be u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Subtracting the integral, or rather the derivative of the integral, is simply going to give us minus v du. And that is relative to dx, of course. And so what we see here is that this term and this term are going to cancel, leaving us simply with, and I'll abbreviate this, u dv. Now, if we recognize the inverse nature of derivatives and integrals, then it should be clear to see that the integral of u dv would simply be our original statement, in this case, uv minus the integral of v du. This right here is our integration by parts rule, which we will be investigating this entire lesson. For our first example, take a look at this integral, the integral of x to the fourth times the natural log of x dx. As much as I would love to do a u du substitution, it's just not going to work here. So what I need to do is integration by parts. Now, recall that this is going to equal u dv. So, in order to do this, I need to choose one of these two factors to be u, and one of these two factors to be dv. U should be the factor that is easier to differentiate, while dv should be the factor that's easier to integrate. I've set this chart up over here, which you'll get used to, for me to fill in the u and dv. Well, taking a look at these two factors, which one of these would be easier to differentiate? Hopefully it's clear to tell that that would be the natural log of x. After all, at this point in time, we don't even know how to integrate the natural log of x, although that will become clear shortly. So I'll let u equal the natural log of x. I'll let dv be x to the fourth dx. From there, I'll go ahead and differentiate natural log of x. That will give me 1 over x dx. And if I integrate x to the fourth dx, of course, that would give me 1/5 x to the fifth. Now, using this information, I can go ahead and rewrite this as uv minus v du. I see my u and v, so I can just go ahead and combine those two together. 1/5 x to the fifth multiplied by the natural log of x minus the integral of v du. There's my v, there's my du. And if I put those together, that will be 1/5 x to the fourth dx. Why x to the fourth? Well, remember this 1 over x took care of one of the x's. This right here is an easy integral to evaluate, so I'll have 1/5 x to the fifth natural log of x, and to integrate this, I will simply have 1 over 20 x to the fifth plus c. And there is the integral of x to the fourth natural log of x dx. In our second example, we're going to attempt to integrate x multiplied by sine x dx. Now, in our first example, we chose u and du based on which factor was easier to integrate, which factor was easier to differentiate. I think you would agree with me that in this situation, it's hard to tell which one would be easier or more difficult. So perhaps we should find another way to determine which should be u and which should be dv. When you're unsure which factor to choose for the u and for the dv, consider using this idea of liate, which I've also heard referred to as I-late. Of course, just reversing the I and the L right there. They're essentially the same thing. This is going to help you choose which factor is easier for you to differentiate. If in your integral there is a logarithmic part, for example, a natural log of some sort, choose that to be the u, because that would be a lot easier to differentiate than to integrate. If there are no natural log or log parts to it, consider using the inverse trig factor to be your u. That will be easy for you to differentiate as well. The arc sine, the arc secant, and all those. If there are none of those, maybe there's an algebraic part to your function, some power of x or a polynomial factor. That'll be easy to differentiate, certainly. Barring that, consider a trigonometric part. And I'm just talking about the elementary trig here. The cosine of x squared or the sine of tangent x or anything like that. And if none of those exist, perhaps there is an exponential part to your function, and you can use that as your u. So if you're not sure which factor of your integral to call u, consider liate, L-I-A-T-E. That will help you determine what should be your u factor. So now that we've investigated liate, that should help us as we return back to our second example here, where we were trying to determine which factor to make u and which factor to be dv. If we follow our liate, we see that there are no logarithmic parts to this. There are no inverse trig parts, but there is an algebraic part, which is just going to be that x right there. Let's make that our u. And then by default, dv will have to be sine of x dx. Having done that, we can go ahead and find du. Of course, the derivative of x is simply dx. And the integral of sine of x dx is just going to be the negative cosine of x. So now that we have our entire chart finished, we can go ahead and say that the integral of u dv, which we certainly have here, u dv, is going to equal uv minus the integral of v du. And all I need to do is just stick my parts in, and we'll have this. uv is, of course, just going to be negative x cosine x. Minus the integral of v du, we have that written right here, v du. That's going to be negative cosine x. Well, negative will make this positive. Cosine x dx. That's an easy integral to evaluate. No problems here. This is just going to be negative x cosine x. The integral of cosine x is, of course, just going to be sine x plus c. And that is the integral of x sine x dx. Feel free to differentiate this yourself and see that you do arrive back at the original problem. Here on the third example, we have a problem that admittedly is going to be quite a bit more difficult than the first two examples. In the first two examples, we had factors, or a factor at least in each integral, that would eventually differentiate and disintegrate down to nothing. Consider if there were a factor of x squared. We could differentiate that to 2x, then to 2, then to 0. It's gone. That happened in both of the first two examples. But it is not going to happen here. If we take a look at our two factors, e to the x and cosine 2x, both of those are cyclical in nature. E to the x, if we keep differentiating, will remain at e to the x. And cosine 2x, if we keep differentiating, will keep alternating back and forth between cosine and sine, without loss of generality, of course. So, we're still going to begin this problem just like we have all the other ones using liate. There are no log functions, there are no inverse trig functions, there are no algebraic functions, but we do have a trig function here in cosine 2x, and so I am going to make that my u, cosine 2x. Therefore, dv is going to have to be e to the x dx. Now, it's not difficult for me to go ahead and differentiate cosine 2x. That would just be negative sine 2x, and then the chain rule, which would give me negative 2 sine 2x dx. And to integrate e to the x dx is also no big stretch. That's just e to the x. So what do I end up with here? I end up with the integral of e to the x cosine 2x dx, u dv, will simply equal uv, which in this case, I'm just going to put these two together. That would be e to the x cosine 2x, uv, minus the integral of v du. There's my v, there's my du. Of course, I have a negative here, so this will go positive. And the 2, I'm actually going to move to the outside. So what I have left inside, e to the x sine 2x dx. In the first two examples, that integral was easy to evaluate. Here, as you see, it is not. In fact, it looks a lot like my original integral, which I needed integration by parts for. Well, I'm going to need integration by parts for this one as well. So, let me go ahead and give this a shot. I need to define my u and du again, and my v and dv. If we use that Lie8 again, there are no log functions, no inverse trig, no algebraic, but we do have a trig function, sine 2x, which means dv is going to be e to the x dx again. Really, I'm just doing standard integration by parts. The derivative of sine 2x, that's just going to be 2 cosine 2x dx. And the integral of e to the x dx will just be e to the x. Where does that put me? Well, let me go ahead and rewrite my function again here. This is going to be the integral of e to the x cosine 2x dx. I'm going to continue with what I had before, e to the x cosine 2x. And now comes my integration by parts fun. In here will be my u, v, just like usual. So that'll be e to the x sine 2x minus the integral of v du. It looks like I'm going to have this kind of thing going on again. So what I'm going to do is, again, I'm going to move my 2 up to the outside. And inside I will have e to the x cosine 2x dx. My writing's getting a little messy. There's a lot to fit here, but this will work out. This is very interesting, though. I have an integral in my problem that looks very similar to my original integral. And I'm going to use that fact to my advantage here. If I go ahead and rewrite everything, this time I'm going to go ahead and simplify these parentheses and this negative and all this garbage over here. This will be e to the x cosine 2x. This will be plus 2 e to the x sine 2x. And then if I distribute this 2 over to here, clearly it'll be minus 4 times the integral of e to the x cosine 2x dx. Now, the fact that I have this integral right here that is equivalent to my original integral, that is going to be very helpful to me. In fact, what I'm going to do is I'm going to add this term over to the other side. Why am I going to do that? Well, it's no use having the problem in the solution. So I really feel that that's going to simplify things for me. And if I do that, look what's going to happen here. This is going to be quite beautiful. On the left side where my original problem was, this is now going to be 5 times the integral of e to the x cosine 2x dx. Over on this side, I'm just going to have what I'm left with after I move that term to the left, which is going to be this right here. Fantastic. These two terms canceled out. These two terms gave me 5 of those. And I'm almost done with this problem. All I need to do now is multiply this by 1/5, which will cause that 5 to go away and give me my original problem. I'll multiply this side by 1/5. And look what I'm going to end up with here. The 5 and the 1/5 cancel, leaving me with my original integral that I was dealing with. Verify that for yourself. There's my original problem. And what is that all going to be equal to? Well, it's simply going to be equal to 1/5 times all this stuff over here. And you might be thinking that there's one thing I've forgotten, but I haven't forgotten it. Right there is my plus c. Did that problem suck? Yeah, kinda. But if it happens where you keep having an integration by parts within your solution, consider this. Consider looking for a term that's the same as your original problem, going through finding a multiple of it, a scalar multiple, and you'll end up with something along these lines. Always a good time. Okay, for example E, we're finally going to get the chance to find out what the integral of the natural log of x is. I know a lot of people have been getting confused about differentiating and integrating the natural log. Here we're going to see what the integral of the natural log of x is. So if we want to solve for y here, this is a differential equation. If we go ahead and multiply by dx on both sides, of course that's going to give us dy equals the natural log of x dx. If I want to solve for y, of course, if I integrate the left side, that will give me my y. On the right side, we have the integral of natural log of x dx. Don't be confused. It is not 1 over x plus c. That is the derivative of x. But we will use that because this is going to require an integration by parts. If we go with our Lie8, the L stands for a logarithmic factor, which we do have here. The natural log of x is a logarithm, and so I will put that as my u, the natural log of x. And you might be asking, well, what can dv then? What can dv be then? What's left here? What's left is dx. All right. So if we go ahead and differentiate natural log of x, of course, that's going to give us 1 over x dx. That one we're used to. And if I integrate dx, I just get x. Well, now we can go ahead and work this out. If we do our uv minus integral of v du, watch what's going to happen here. U times v is simply going to be x multiplied by the natural log of x. And our integral of v du, in this situation, v du, well, the x and the 1 over x are going to cancel out. I mean, I could write it like this if you like, but the x and the 1 over x are going to cancel out, leaving me with just dx. And of course, we know the integral of dx is just x. And so the integral of natural log of x dx is equal to x natural log of x minus x plus c. Anytime you need to, you can figure that out using integration by parts. But I will tell you, that is a very, very handy integral to just memorize. The integral of the natural log of x dx is x natural log of x minus x plus c. In example F, we're finally going to get the opportunity to use integration by parts to evaluate a definite integral. So we are going to end up with a number as our answer here. Of course, we're going to handle it still the same. We have the integral of x secant squared x dx. And while I would love to do a u du substitution, it's just not going to work here. So to do my integration by parts, let's think about Lie8. There are no log parts. There are no inverse trig parts, but there is an algebraic part in my x. So that is what I'm going to let be u. dv, of course, then is going to have to be secant squared of x dx, which if you've memorized all your trig integrals, that's a very, very easy one that you should remember. So to get du, the derivative of x is simply dx, and the integral of secant squared of x dx is just tangent x. That's easy enough. Now, remember that the integral of u dv is going to be uv minus the integral of v du. That's not too bad here. Uv is simply going to be this x and this tangent x. I'll stick those together and get x tangent x. which is going to be evaluated from 0 to pi over 4. This next part is going to be minus the integral of v du, and that's not too bad either. That's just going to be tangent x dx, which, again, if you've memorized your trig stuff, that's not too difficult. So let's go ahead and evaluate this part of the integral first. Of course, this should have the bounds on it. But if we go ahead and evaluate this, this is simply going to be pi over 4 multiplied by the tangent of pi over 4 minus 0 times the tangent of 0, which means that this first part is simply going to be pi over 4, no biggie. Now over here, certainly you remember what the integral of tangent x is. That's going to be negative, well, we already have a negative, so that's going to make this positive, the natural log of cosine x. You remember that, right? That's going to go from 0 to pi over 4. And so if I deal with that, I'm going to get the natural log of cosine pi over 4, that's square root of 2 over 2, minus the natural log of cosine 0, which is 1, and of course the natural log of 1 is 0, so that's gone. What do I end up with for my final answer? Pi over 4 plus the natural log of square root of 2 over 2. Now, I know some of you like to simplify things, break down your logarithms and all that good stuff. If you're one of those people, then it is foreseeable that you would end up with something along these lines. The square root of 2, of course, is 1/2 natural log of 2. There's for the 2 on the bottom. And if we simplify that just a little bit more, again, I don't know why you would do all this, but, you know, if you just like this kind of torture, then you would end up with this as your final result of our definite integral. For our last example on this lesson, I would like to introduce you to the tabular method of integration by parts. In a situation where one of the factors will eventually differentiate down to nothing, but the other factor is cyclical, the tabular method provides a great way to quickly find the integral. On example F, you see we have x squared cosine of 2x. The x squared over time will differentiate down to 0. Think about it. X squared goes to 2x, goes to 2, goes to 0, and it's gone, as we discussed earlier, while the cosine of 2x is going to just keep going around cosine, sine, cosine, sine. If you choose to do the integration by parts, which I certainly recommend you try, you can see I tried it here, and it's not terrible, but it is kind of a pain in the butt. It works out eventually, but why go through all the work if there's an easier way to do it, which the tabular method is far, far easier. So let me show you how the tabular method works. What we're going to do is we're going to set up 3 columns. We're going to have one column called signs. Easy enough. That column is just going to start with a plus, and it's going to go to a minus and a plus, and it's going to keep alternating down as we go and go. Whatever factor I would choose for u, that's going to be my second column. So think about it. In this situation, which factor would be u? I have an x squared. I have a cosine 2x. Well, if you follow your lie-8, u will be that x squared. And all I just keep doing is just keep differentiating x squared to 2x, to 2, and then to 0. Looks like I'm going to have 4 rows on my column, or on my table here, so I'll add that in. Finally, let me go ahead and label my dv. dv is, of course, just going to be the other factor, in this case, cosine of 2x. And all I need to do is keep integrating that cosine of 2x. My first integral of that will be 1/2 sine of 2x. My next one will be negative 1/4 cosine 2x. And I can keep going on this. I will then have negative 1/8 sine 2x. And you can see this is never going to go away. But once I have it all set up in this manner, all I need to do is go across and then down like this, and these will give me my factors. My first factor of this integral is simply going to be 1/2 x squared sine 2x. Observe where I got that from. It was positive, my x squared, and my 1/2 sine x. My next factor, or term I should say, is going to be this right here. That's going to be plus, yeah, I know it says minus here, but it also says minus here. So that is going to be plus. The 2 and the 1/4 are going to give me 1/2. I still have my x, cosine 2x. Notice that I had an x squared. Now I have an x. My next term is going to be this right here. There's no x's left. In fact, this term is going to be minus 1/4 sine 2x. I could keep going, but here u has hit 0, so it doesn't really matter what's left. It's just going to zero out anyway. So I have all this. I can go ahead and add my plus c to it. And if you did try doing this using integration by parts the standard way, you should get exactly the same answer as you see with the tabular method. Quite impressive. The tabular method, remember though, only works when one factor is going to disintegrate down to nothing, while the other factor is going to be cyclical in nature. Be wary of that, be careful, and good luck with your assignment 7.2.